So, good morning, everyone. My name is Siyu Chen, and Rafael has just introduced my research topic. My today's speech will about cloud-based multidisciplinary and multi-user BIM system for concurrent engineering design. So the content is divided into 6 parts: introduction, scientific background, hypothesis and objectives, research methodology and plan, work done to date, significance and contributions. So let's get started. As we all know, modern building design requires close collaboration between architects, engineers, contractors, fabricators, builders of diverse professional backgrounds for the design, procurement, construction, and so on. And to encapsulate and generate, store, or exchange the information, the professionals use various kinds of technologies to design, to realize these goals. And these technologies have been improved over time in the AEC industry. So the state-of-the-art technology for building design is building information modeling, short for BIM. And then let's have a look at how BIM model look like. So the left-hand side picture is a Microsoft building in Herzliya. And then the right-hand side picture is the integrated BIM model of the same building provided by a company called Technion, which was the contractor of this project. So from this picture, we can see how far we can go with BIM, combining 3D digitized model to represent multidisciplinary design information in addition to the geometric data. And based on this, the effective integration of multidisciplinary design information can be achieved and passed on for the subsequent task use, such as the procurement, maintenance, operation, construction, and so on, and also reducing the project delivery time, decreasing the project cost, increasing the productivity and quality, and eventually makes the sequential engineering in the AEC industry better. So what is sequential engineering? Sequential engineering, also known as traditional engineering, is a process where each stage of the development is carried out separately, and the next stage cannot get started until the previous stage is finished. That means in the building design, the BIM cycle design, life cycle design and construction process is development procedure which carried out one after another, then centering around one single domain of expertise at a time. However, BIM is not the culprit of sequential engineering. The major reason of the sequential engineering in this AEC industry is the fragmented nature, such as the isolation of the professionals, the lack of the coordination between design and construction because it is carried out in the sequential manner. So it is proof that sequential engineering is not enough for today's industrial pressure, and there are still some specific limitations need to be fixed, such as a lot of rework and duplication on the design model, and then the delivery delay due to the too much coordination seeking for the approval for the model changes, and also the client's requirement cannot be well defined at the very early stage of design. And all of these limitations eventually lead to the dissatisfaction from the clients because the cost, quality, and performance of the construction project cannot get guaranteed. Therefore, we know the definition of the sequential engineering and the limitation of it, so that we can let's think about the current design paradigm. It is developed in the framework of sequential engineering, and the vendors generated the software according to the way people are working, which is sequential engineering, so that we can interpret that the software generated in the sequential framework doesn't allow better collaboration on BIM, or we can say it's limited in collaboration enhance. Therefore, many researchers propose to introduce the concurrent engineering approach into the AEC industry. What is concurrent engineering? It is a methodology of designing and developing products, emphasizing parallelization of the task. And the philosophy of it is to promote the incorporation of downstream concerns into the upstream phases of the development process. And as you can see in the picture, compared with sequential engineering, concurrent engineering can lead to the shortened development time, improved product quality, lowered development production costs, and then eventually enhance the collaboration. Therefore, I would like to introduce the concurrent engineering approach into my research to enhance the collaboration. However, it might be a too big topic if I focus on the whole BIM lifecycle. Therefore, we need to find a point to narrow down it. The McLeamy curve provides us this opportunity to narrow down the scope. As you can see on the picture about the red line, the cost of the design changes becomes more and more expensive along the time. And that illustrates that a construction project become more difficult to change the more developed it becomes. And if you look at the blue curve, you can see that it's the effort spent on the design phase is preferred over downstream phases. And this requires the production information should be maximized in the early design phase. And it just having to justify the concurrent engineering's philosophy, as we mentioned just now. Therefore, we decide to narrow down the research scope into the design phase. Okay, then let's take a look at what people are, how people work in the design phase. So basically, it's still a sequential practice. And in the project, in a construction project, the architect's team will produce the architectural model or design first, and then pass all the documents or information to the structure engineers for generating the structural model. And at the same time, or after that, this is the two pattern, all the information will pass to the MEP engineers for generating the MEP model. And this is just the main step. And the most complicated part is that they will still need to do a lot of design changes, and this design changes need to be fixed, coordinated, and it will take a lot of time. So it might be a little bit confusing that the first pattern, it seems that they're doing concurrent engineering. Why? Because it seems like the structural model and the MEP model are being done at the same time. But actually, it's just helping the sequential engineering better, because they still need to wait until the architectural model has been done, then to start their work. So, in other words, it's just helping with the sequential engineering's collaboration. But is that opening up the door for the concurrent engineering? Not so much, because they are not able to adapt the change, and then there are no updates when they are making change. And they prefer to wait the architectural models down, then pass to them, because they don't want to have the change made when they are doing their own work. So basically, currently, in the BIM design phase, it is still, the BIM is still used for the visualization, clash detection, and model design instead of real collaboration and coordination. Therefore, this research is about to introduce the concurrent engineering into BIM-based design and development process, including both design editing and coordinating. I will call it concurrent design. So I think this will be a good solution because it's potential to be able to provide a scientific methodology to create a new paradigm for the design phase. And then based on this paradigm, we can elicit the requirements for BIM technology to develop new tools for the better collaboration. And then eventually is the industrial pressure. So far, we have narrow down our research scope into the design phase and then clarify that we need a new paradigm. And now next step, I will show you the feasibility about this research by showing you the some type scientific background from these three aspects. So first aspect is the development of concurrent engineering, and I will analyze why do we need concurrent design. And then we will look at some few limited cases related to concurrent design in the AEC industry and to analyze the limitation of it currently. And at last, we will look at what kind of technologies is promising to support this kind of concurrent design in AEC industry. So the first part is the development of concurrent engineering. It was coined in the late 1980s, and then the principle had matured in the next 2 decades. It has already been implemented successfully in the manufacturing industry, and then so that the researchers in the AEC industries propose to introduce it in our own industry. But it hasn't been implemented in this industry. Why? There are two kind of inhibitors. One is from the organizational aspect, that the fragmentation in the AEC industry is the major problem, and it's related to the people, the policy stuff, like the contract forms and the way people get employed. And I'm not dealing with these questions because it's out of my research scope. And I would like to solve the problem from the technological point of view. It's related to the problem like process and the technology. So that means we need a paradigm for design new tools. However, it's very limited, and there is not too many concurrent engineering model and tools in this industry. While big room design is a quite classic way to do the concurrent engineering, but it's not sufficient currently, because what is big room design? We can look at that picture. Is that we gather all the team members from different disciplines into one room, and then we will talk about how to do the project. And why do they want to sit in one room? Because they can just go and discuss one on the other immediately. It's kind of achieved more on the concurrent engineering, and it's an option for helping the collaboration. However, it's not always feasible, because it's not always feasible to gather all the people from the different locations, different disciplines at the same time in one room for several days. And even it's possible or feasible, it's still, the communication is still verbal and paper, so that we can interpret from that. People cannot do a proper collaboration by using their own tools at this point. Therefore, we need tools in the concurrent engineering framework to enable concurrent design. So now let me show you some limited cases related to concurrent design in the AEC industry. Back to 2003 is quite early. Smith has proposed some requirements for the collaborative conceptual design, and the concept of design intent is quite an impressive study, considering it's 20 years ago. However, it's limited to the conceptual design phase. And also, it's limited to it's more like provide the requirements for communication rather than editing and coordinating on the same platform. Therefore, according to the previous requirements, there are more and more platforms, common data environment platforms has been established, both in the industry and academia. Industries is like BIM 360 and Tekla Project Viewer, and also many research-specific prototypes for the multidisciplinary team to update information. But it's still limited. Again, it's limited to the communication rather than real editing and coordinating for the design. So we can conclude here that firstly, the framework for this concurrent design, the paradigm is not clear yet. And for the tools, there are still many other ways to improve it under the concurrent engineering framework. So for the tools, we have some promising technologies to support it, and many researches have been done showing that the cloud technologies is convincible to manage and exchange design information concurrently, and also it's able to enable other technologies like virtual reality, semantic web technologies, and also machine learning. And for the semantic web technology, it's also promising for enriching the relationships and the constraints among objects. For the machine learning, the research also shows that it's able to facilitate the semantic enrichment and intelligent design in BIM. So based on the scientific analysis, scientific background analysis, I concluded the knowledge gap as the following. The first one is there is not a comprehensive knowledge framework or paradigm has been studied for BIM-based concurrent design in the AEC industry. And the second one is that many researchers prefer to use new technologies with old methodology, saying sequential engineering, rather than adopt a new methodology, concurrent engineering with new technologies. It might be a little bit abstract here, so I will give you a metaphor. Imagine that we have a problem, not imagine, it's true. We had a problem with the petrol car fleet, and it released a lot of carbon emissions every year. So people figure out the ways of making the catalytic converters for the exhaust pipe or something else to filter the smoke. Then that's one way to release the problem. But there is a better way that we can use electric cars. Then we can be environment friendly. So fixing the IFC or interoperability problem is kind of like you are fixing something in the petrol car engine. But if we say we go for the concurrent engineering directly, that means we don't have to deal with anything with the petrol car, and that's a completely different approach than just fixing the data exchange problem in the sequential engineering. And the third gap is that to date, there is not a multi-user and multidisciplinary BIM-based editing solution for concurrent design in the AEC industry, instead of the common data environment, which doesn't allow editing, at least currently. And the last one is the emerging technology like cloud, semantic web, and machine learning are promising to support BIM-based concurrent design. But due to the sequential framework, it hasn't been fully utilized in this industry. So to fill the gap, we raise up some questions to ask myself that what features and functions does BIM-based concurrent design require in the AEC industry? And what kind of environment and technology could support these features and functions? Specifically, what data representing are needed, and what kind of properties in this data representation are we needed to support these specific features and functions. And second, how can versions be managed and visualized since you are doing the editing and the coordination with others concurrently? And the last, how can this tool interact with users to interpret and display the design change proposals that originate in the BIM system of other users whose data schema is different? That's a lot of questions to answer. So we're trying to explore the answer based on the hypothesis that, first of all, current BIM paradigm doesn't fully support concurrent engineering. That's the biggest motivation of my research here. And then it is possible and feasible to create the multidisciplinary and multi-user BIM system for concurrent design. And that's the biggest assumption here, because if it cannot happen, then I will not do it. Okay, at least it's feasible and possible according to my scientific research. And thirdly, such a system could shorten the construction project delivery time and improve the design workflow by increasing the information availability. And this is related to the significance of this research. Now, according to the questions and based on the hypothesis, the overall goal is identified to explore the mechanism, including the features, requirements, and the feasibility principles for a concurrent, multidisciplinary, and multi-user BIM editing solution. And in order to achieve this goal, several specific measurable objects must be met. The first one is to create a paradigm for the BIM-based concurrent design. Then the second objective is to determine the feasibility of this paradigm by testing some prototypes. And then the third one is test whether this emerging technology are useful or essential in the BIM-based concurrent design. Now, welcome to my research methodology and plan. My research methodology adopts design science methodology. Then the first step would be the identify the problem, then define the objectives, design and development, demonstration, experiments, and optimization. And according to this methodology, I made the research plan like this. So here, I think the problem we have already repeated for several times in different formats. So what do we need for creating such an editing solution? And then this is 3 objects. I will explain in detail how can I realize them. So to answer that overall question, the first objective need to be realized is to create the paradigm for BIM-based concurrent design. This requires me to identify the requirements and features, and then design the use scenario according to the requirements. And for the demonstration part, I will do the functional mockup by designing user interface mockup by the Actual. Actual is the user interface design tool for creating prototype. And then at last, for the experiment, I will refine the requirements by illustrating how the system feature might work and form the focus group to elicit the responses of design professionals and obtain and refine the requirements from their perspective. And the next objective I want to realize is that to determine the feasibility of the paradigm we created in the last objective. So for doing this, I need to design the use case and then design the prototype according to the use case as a window application by adopting the GPU-intensive multiplayer game technologies. And then to implement for demonstration and evaluate the prototype by designing the inter-domain testing scenarios for two groups of experts. One group will use the current BIM tools, and another group will use my prototype. And then the last stage will be evaluate the prototype by measuring the efficiency and effectiveness, both based on both the qualitative and quantitative analysis. And the last objective would be identify the essential technology for BIM concurrent design. To do this, basically I will need to integrate new features into the current BIM system by design some APIs. And then I will implement it for the experiment. This experiment will test whether the concurrent design can be achieved simply through integrating consistency function within the APIs of current BIM tools. If yes, then copying the domain models into cloud might not be necessary, because the current BIM paradigm can already support this kind of concurrent design. And then that might be my final product. But I wish if not, that means there are a lot of technological gaps between the current and the ideal concurrent design. And then the next step will be to illustrate the CBIM could be the solution to the concurrent design. That will take you to my colleague's work, and which will be explained in detail in the later on lecture. So let's see what I've done so far. Basically, I've already completed the first task, except the iteration part. And then this task is for identifying the requirements and the features for the BIM concurrent design. I conducted this task in two ways. The first way is, of course, literature review, and the second way is to watch the recorded interviews conducted by Trimble, user experience team in the US, and then read the interview analysis report of Eva in the Trimble UX team Finland. So basically, there were 19 interviews have been conducted by Trimble, focused on the early adopters of BIMs from different disciplines in the US companies, for painting a picture of a perfect future for construction project collaboration. And based on this, I propose an initial conclusion that for the requirements that for the BIM-based concurrent design, all participants should be able to simultaneously view and manipulate the objects that compose a building. So specifically, this requires that when one user makes a change, the change is propagated to all other users across domain. So let me give you an example here. If a MEP engineer makes the section of a pipe or a duct larger, the size larger, then the opening on the floor or on the wall, in the structural or architectural model should also get enlarged right after that. And yes, and then second one is the concurrent design also requires the changes must be managed through a formal authorization procedure that respects the design responsibility of users. So what does that mean? Obviously that everyone should take responsibility of their own model, their own design. Even you can propose the change to each other. However, you still need to wait the approval from the owners, then you can get the change done. And then thirdly, this concurrent design also requires visualization and status control of proposed design changes as they progress through the authorization procedure. Also, what does that mean? That means when a change is being processed, the users will be able to see the status and the progress. For example, if I made a change in my own model, which is related to the structure engineer's model, then I would able to see the status that if I propose that and then he get that, but he haven't checked it, or if he has already checked it but hasn't responded to it, or he has responded as rejected with some reasons, or accept it completely, or accept it with some modifications, I will be able to see all the progress and the information during the authorization procedure. And then last, the concurrent design also requires the ability to manage and store multiple versions of design alternatives at the level of individual objects, systems, or parts of the buildings or of the whole buildings. What does that mean? Because usually if we have some design alternatives, even it's very tiny modification, we still need to save it as a file. And that's a little bit not that smart, cumbersome, and also resource wasting. So that we come up with a platform that can enable we store all the design alternatives in one model. And that's basically my initial requirements for the concurrent BIM-based concurrent design. Then I have already designed the first use scenario called interdomain change propagation. Remember the Microsoft building I showed you at the very beginning? I took a section of the building, and a small part of this section, there is a staircase, and we modified it into a very simple building. But I know it's not a perfect building, but it's easy to understand. We're trying to make it easy to understand. So this two-floor building starts from the ground floor, first floor, and then the second floor. Just try to make it clear. Then, as you can see on the first floor, there are two areas. One area is for library, and then another area is for the office. So originally, it is a whole slab, but in different colors. Then, due to the large life loads in the library area, the slab in the library area needs to be 50 millimeters deeper than in the office area. Okay, so the structural engineers split the slabs into two parts, as you can see in the picture, and also make the slab thicker upwards by 50 millimeters, as you can see on the right-hand side picture. And so far, the changes in the structural model has been done, and it's saved as the temporary status. Remember, temporary, because this change is related to the architectural model. And then we come to the architectural model view. The architect gets the notification, and the system knows that what the structure model has been changed. And the system split the floor for the architect automatically, split the floor into two. But the system cannot decide the permutation of the floor layers because it's more complicated than just split the floor. Basically, here we have two layers of the floor. The top one is the decorative layer, and the bottom one is the concrete layer. The concrete layer is also known as the slab in the structure model. Therefore, the system come up with 4 options out of different design intents. The first option is that I want to keep the floor thickness fixed so that, and then aligned with the structural engineer's change. So here they raise up they make the concrete layer 50 millimeters higher, and then reduce the decorative layer by 50 millimeters so that they can keep the thickness fixed and also keep the bottom and top surface aligned. This is the recommended option. And the second option is to keep the floor height fixed. That means the space from the distance from the top surface of the floor to the ceiling will be maintained. Then the decorative layer also want to be fixed so that the system come up with option to make the concrete layer thicker downwards by 50 millimeters, as you can see in the picture. And the third option is to, out of some reason, then it makes the concrete layer thicker upwards by 50 millimeters. And then the last one is to keep the, they make the concrete layer thicker both upwards and downwards by 25 millimeters. It seems that the first one is the recommended one, and the third one is not bad, but let's try to make some drama. And the architect is the rebel. He says that I just want to use the third option. He said, I don't have to change anything. I can keep the decorative layer fixed and I can get aligned with the structural engineer's change. So I'm kind of lazy. I just want to do this way. Okay, no problem. But when he clicked the button, it failed. Why? There is the conflict, but it's not from the structure model. It's from the MEP model, because there is a constraint from the client saying that, okay, I want all the socket outlets should be at least 500 millimeter higher than the surface, the floor surface. However, we raise up the surface by 50 millimeters so that the distance in between becomes 450 millimeters. Now the architect says, okay, I'm waking up. I choose back the recommended one. And now everything is fine. The distance in between turned into 500 millimeters again. And no clashes anymore, no change propagation anymore. And everyone is happy now. So at this point, the structure model's temporary states has been changed into the conform status. Okay, then period for this use scenario. And it also comes to the end of my research. No, not research, lecture. Sorry. Okay. If I can conduct the research successfully, it will eventually break the limitation of the current BIM paradigm that people work on different software tools sequentially with poor interoperability and coordination problem. And then second, I will probably use and combine the emerging technologies like semantic web, machine learning, cloud BIMs into this traditional industry in the framework of concurrent engineering. And the third one is practical, meaning that I hope it will shorten the whole delivery time of construction projects and reduce the construction cost. Then come to my expected contributions. The first contribution will be that the research will contribute to the body of knowledge in the AEC area by identifying the requirements, features, and supports for the BIM-based concurrent design, as well as by creating new paradigm for it. And second, I will provide a prototype for interactive experience of concurrent design in the new paradigm. And next one is to provide a stepping stone for the developing new insights and understanding into concurrent design through the multiplayer game interface. And the last one, I will provide an alternative perspective to enhance the BIM collaboration by adopting concurrent engineering. period. So